Good afternoon. Today we're going to go over Fourier series, in particular series that involve both sine and cosine functions. So this is actually necessary if the function to start with is neither odd nor even. Let me remind you briefly that what we went over up until this point, when we talked about Fourier sine and cosine series, basically these series will represent functions which on the interval minus pi are either odd or even, depending on the case. So just to briefly recall the main concept here. When we talked about a Fourier sine series, which looked like summation from 1 to infinity, an sine of nx, these will basically cover functions that if you look at the interval minus pi, well, I mean, we started with the function on the interval 0 pi. So let's say that function looks like this. And then the Fourier sine series for that function will represent not only the function in the interval 0 pi, but also its odd periodic extension. So it will cover automatically this portion of the graph reflected over or symmetric with respect to the origin, and of course the periodic extension left and right over the period 2 pi. Once again, there's nothing special about the interval minus pi and pi. We're going to extend that to any symmetric interval. But bottom line is, because sine is an odd function itself, these essentially will cover only odd functions on the interval minus pi, or on a symmetric interval in general, as you will see later when we move on to more general, to generic symmetric intervals. And consequently, if you talked about a Fourier cosine series, which, to use the notation that we have in the formula, it looks like a constant outside the summation, and then summation from 1 to infinity, an cosine of nx. And remember, the reason we have that constant outside in the form of a naught over 2 is for convenience with the formula. This type of function will represent, again, once we built it to represent a function on the interval 0 pi, let's say it looks like this, it will represent also its even extension. So basically the same shape reflected over the y-axis, and then periodic extension left and right for next intervals of length 2 pi in this case. So I want to say this one more time before I move on to the main topic of today's lesson, because people sometimes are still confused with having the same function to start with. Let's say I start with the same function between 0 and pi, and yet one series represents a completely different function if you extend it outside that interval, right? So whether you use the sine series or cosine series, that matters, right? The sine series, so I mean, sine and cosine series both will represent the function to start with between 0 and pi, but each of them represents a different type of extension, periodic extension. One of them is an odd extension, the other one is an even extension. And bottom line, if you have only a sine series, then you can only talk about odd functions, because the sine itself is an odd function, and of course here we have even functions. So this will cover only even functions. And also, as a quick reminder, the mathematical definition for an even or odd function, if you have a function that is defined on a symmetric interval, let's say minus c and c, f is odd if f of minus x is equal to minus f of x for every x, and it's even if f of minus x is equal to f of x for every x in that interval. We need to take a symmetric interval because we need the function to be defined at both x and minus x, so at both sides of the origin, basically. All right, so then what do we do? Let's write down as a motivation then for this lesson. What do we do if we have, so what do we do, the question mark, if we have a function on a symmetric interval that is neither odd nor even. So as an example, which I'm gonna deal with it later, let's say your function is equal to, we're gonna make it to be like piecewise defined function. Let's say it's 0 for x between minus pi and 0, and x if x is between 0 and pi. So if you were to sketch it, it'll look like this. Minus pi, 0 on the first half, x on the right half. Okay, so notice that we can take the function on a half the interval and use symmetry, because it's neither odd nor even. Right? The only reason we could build the formula for the representation of coefficients in the Fourier sine and cosine case, the reason we can take it for a half the interval is because the function is symmetric, and there's a relationship between the integrals between 0 pi and minus pi 0. We'll get to that later, but here it's not symmetric, so the starting point, it's not 0 pi, but the actual symmetric interval about the origin, like minus pi and pi in this example. So what do we do in this case? Well, there is a nice little trick which states that any function, so let's write it down. So any function defined on a symmetric interval can be written as the sum of an odd and even function. So actually things are much easier than you may think. We basically we use what we learned before and split the function into an even and odd part. And if I want a series representation, we simply put in the sine series representation for the odd part and the cosine series representation for the even part. And that's the reason why when we have these type of functions that are neither even nor odd, and we want a series representations, that requires both sine and cosine, as I mentioned here in the title. And another good news is that to produce this even and odd part, it's actually pretty easy. You just have to basically know the little trick, which I'm going to explain right now. So how do you make up these even and odd parts? By the way, sometimes these even and odd parts are pretty obvious. Let me give you an example. So, obvious examples. So let's say I have a function f of x equal to x plus x squared on the interval minus 1, 1, let's say. So it's clear that this is the odd part, that's an odd function, and this is the even part. So you see it immediately when you write down the function that it's actually a summation between an odd and an even part. I hope it's clear why x is odd, right? I mean, if you sketch x as a function between minus 1 and 1, obviously it's symmetric with respect to the origin, and then x squared between minus 1 and 1, it's symmetric with respect to the y-axis. So sometimes we don't even have to do anything fancy. We can already see in the problem which is the odd and which is the even part. But sometimes that's not obvious, especially if the function is piecewise defined like in my example here. So here's a recipe of how to construct the even and the odd part. Let's say f of x is given, right? The given function. So construct two related functions. One of them, let's call it g of x, which is going to be defined as the semi-sum of f of x plus f of minus x. So f of x plus f of minus x over 2. This is the even part. The odd part, I'll write it down immediately, and when you add the two, you will get basically the original function, as you'll see immediately. And the second part, the odd part, is the difference of these, f of x minus f of minus x over 2. That is the odd part. All right, so take a moment if you want to pause, if you want to catch up. Write this down. And then we're going to quickly show, and I think I'll have room on this page before I move on with an actual example. I can quickly show that they satisfy the conditions, right? So remember, what I want is an even function and an odd function such that the sum of the two gives me the original function, right? So the f of x is the given function here. And then I'm going to check quickly that each of them is, as I mentioned, g of x even, h of x odd. Let's check that the sum of the two is indeed f. I hope you can even visualize this, right? So if you add g of x and h of x, the way I define them, notice that f of minus x cancels. So you're left with 2f of x over 2. So indeed, indeed the sum of the two gives you the original function. And notice that g is even. So if I replace x with minus x into the g of x, well, that's going to be f of minus x plus f of minus minus x over 2. But that's just the same thing. All right, so g of x is even. If you replace x with minus x, you get the same thing. And here in the case of h of x, if I replace x with minus x, I'm going to get f of minus x minus f of x, right? Because that's minus minus x. But that's nothing but the opposite, if I pull the minus out, the opposite of the original. So minus h of x. So this is the simple recipe of coming up with the even and the odd part. So on the next page, I'm going to show you how to actually come up with a Fourier series for the example. I'm going to actually write down the Fourier series definition overall, how it looks like, and I'm going to use the previous example with that piecewise defined function mentioned here in the middle of the page to come up with its Fourier series, just using the tables, because at this point, although I'm going to provide a formula for the coefficients just like before, once we have tables, we have to make use of them as much as possible to save time. So stay tuned for the next page. So actually, before we come up with the example, let's come up with the formula for the coefficients, just like we did before for sine and cosine series. So once again, at this point, we know how to split a function into an even part and an odd part. Okay, so remember, g of x is going to be f of x plus f of minus x over 2. And h of x is the difference, f of x minus f of minus x over 2. So if I want, and let's say again, just like before, that x is between minus pi and pi. If I want a Fourier representation, so the Fourier, by definition basically, the Fourier series of f of x is simply the sum between the sine series of h of x. I'm going to start with that. That's the odd, well, I'm going to start with the even part, but the sine series is for the odd part. So the sum between the sine series of h of x and the cosine series of g of x. So basically your f of x will be a naught over 2, so I'm going to write down the cosine series for g of x. A naught over 2 plus summation from 1 to infinity an cosine of nx. That will replace essentially g of x plus the summation from 1 to infinity. We're going to have to name the coefficients differently. Bn sine of nx. And that'll replace, of course, h of x. And sometimes it's customary actually to write, in fact, not sometimes, always, it's customary to write these into a single summation. Because you want a series representation for a function, that means you need to provide an infinite sum. One of them, right? Not two of them. So you basically combine the two summations into one. An cosine of nx plus bn sine of nx. Now remember, we need to know how to compute these coefficients. But I want to pause the video for a moment, and if you need to catch up a little bit and realize that we know already how to do this. This isn't basically from this point on a new lesson. We know the formula for a cosine series of g of x. What's the formula for the coefficients? Well, an will be the integral from, 2 over pi, the integral from 0 to pi g of x cosine of nx. Now notice I'm taking it between 0 and pi because the function is even on that subinterval. And then bn will be 2 over pi, because that comes from the sine series, 2 over pi, the integral from 0 to pi h of x sine of nx. So we can leave the formulas like that. However, it is customary to provide formulas for the Fourier coefficients in terms of the given function f of x. Let's imagine that you have a given function. You don't have tables for its even and odd part. So let's say you don't have any serious tables at all. Then it would be useful to provide a formula for the coefficients for an and bn in terms of f of x, so that you can bypass finding the even and the odd part. This is just a matter of convenience. Often it's not really that huge of a deal to come up with these coefficients. To this even and odd part. But again, it's customary to provide a formula in terms of the given function, just like we did for the sine and cosine series. So I'm going to show you a little proof. Most of these proofs, by the way, are not required to be memorized, but often, if it's not so long, I prefer to give proofs of many of these concepts just to see where they come from. So I'm going to show you the proof for the formula for the coefficient for an, because the formula for bn it's very similar. And then I'll give you the example that we're going to use with the table. So in order to do this, to find a formula in terms of f of x, we're gonna have to use basically a little change of variable. So let's start with an. We're gonna replace g of x with its version in terms of f of x. So g of x, remember, is 1/2. Let's write it like that: 1/2 f of x plus f of minus x cosine of nx dx. And if you move 1 over 2 outside, 2 cancels with 1 over 2, and this is going to be 1 over pi, and I'm going to break these two integrals into two pieces. 1 over pi, the integral from 0 to pi f of x cosine of nx, plus the other piece, 1 over pi, the integral from 0 to pi f of minus x cosine of nx dx. All right. So we're going to leave the first part as it is for a moment. And on the second part, we're going to make a little u substitution, just because we want eventually to be everything in terms of f of x. So let's do I'm going to call it y. I mean, it doesn't matter, u, y, it's the same, just a new variable. So let's make the substitution y equals minus x, which means that dy is minus dx, or dx is minus dy, if you want. And the new bounds in y, so if x is 0, the lower bound of y is 0, and if x is pi, the upper bound will be minus pi. All right, so let's continue. Again, we copy the first part. And the second part becomes now the integral from 0 to minus pi, and minus x becomes y, and x inside the cosine and x becomes minus y, right? So it's going to be minus ny inside of that cosine, and dx becomes minus dy. All right. And now another property of Riemann integrals. Remember, if you change the sign, like if you put let's put it differently. If you interchange the order of the bounds, so if instead of 0 to minus pi, I have from minus pi to 0, you change the sign of the integral. So I can get rid of this minus dy, so that minus, by simply interchanging the order of the bounds. Okay, so these are properties of Riemann integrals, if you remember from calculus 1. So that's now the integral from minus pi to 0. The minus from the outside disappears. And remember, cosine is an even function. So that means cosine of minus ny is the same thing as cosine of ny. So the second piece of the integral now is from minus pi to 0 f of y cosine of ny dy. But remember, you can name the variable of integration however you prefer. You can go back to name it x again. This is essentially a substitution that doesn't change anything, right? And because you just change the variable. Sometimes people call it the dummy variable because it can be named however you want inside the integral. That's just to make it again in agreement with the first piece, dx. So now you can recombine these two integrals because now you have integral from minus pi to 0 plus 0 to pi, because if you factor 1 over pi, you have the integral from minus pi to 0 of a function plus the integral from 0 to pi of the same function. Right, so that's like integrating over an interval, but first half plus the second half, right? So imagine you have the interval minus pi, pi and 0. The integral over this plus the integral over this is the same as the integral over the whole interval. So I can write the whole thing into one nice single integral from minus pi to pi, f of x cosine of nx dx. So I'm going to write down these formulas on the second page, I mean the next page. We're going to provide the formula for Bn right away. I'm not going to redo the same thing because it's very similar. But we're going to have these formulas, we're going to compare them with the formulas for the sine and cosine series before. And then finally we get to the example that I promised you earlier. So stay tuned for the next page. All right, so take the moment to write it down again. So the Fourier series representation for a function on the interval minus pi, pi is given by essentially a summation of a series in cosine and a series in sine. Put it together like shown here on the top of the page. The formula for the coefficients, again, something you need if you don't have tables of Fourier series already. The formula for the coefficients is 1 over pi, the integral from minus pi to pi, f of x cosine of nx for a n. Here n starts from 0, 1, 2, and so on, because you need to take into account the a naught on the outside of the summation. And bn is 1 over pi, the integral from minus pi to pi, f of x sine of nx dx. So I'm going to go over again with a comparison with formulas for Fourier sine and cosine, because again, sometimes people are still confused why you take just from the interval 0 pi. I'm just going to mention here one thing that you got to realize that if the function is even or odd, then this integral can be taken only on the right half of the integral, because on the other half the integral is the same essentially. And I mean, it's not the same, it's twice as much basically, so you don't need to take the integral over the whole interval. Here we take it between minus pi and pi because again the function is not symmetric, it's neither even nor odd. I'll get into that more details in a different class maybe, because I want to go over the example now and maybe be done for today. But again, at this point, keep in mind the starting point for a function that is neither odd nor even is just minus pi and pi, or any symmetric interval for that matter. But if you deal with a function with a cosine series or just a sine series, the starting point in that case is the right half of the interval, or 0 pi in that case. So let's see how we do an example, not with these formulas. Maybe we'll do it in a different lecture, one example directly with the integral. Let's do one with the actual table. So let me go back to the example that I provided on the first page. So let's say f of x was 0 on the interval minus pi and 0, and x on the interval x pi, 0 pi. Right, so that looks like this. And let's not do it with the formulas, but with the tables eventually. So let's come up with the even parts so that hopefully we can find from the table the Fourier cosine series for the even part and then the odd part. When you have a piecewise defined function, you got to be a little bit careful here not to make a mistake when you combine these functions. So the even part, remember, is the semi-sum of f of x plus f of minus x over 2, and the odd part is the difference between the two over 2. And in both cases you need f of minus x, so you need to compute f of minus x and then write it in the same manner as f of x, which will entail that in the end maybe interchanging the output of the function. But first, replace x with minus x everywhere. So look at the definition of f of x. So f of minus x is going to be 0 if minus x is between minus pi and 0, and minus x if minus x is between 0 and pi. So here, if you multiply by minus, because you need to basically write down in terms of x these inequalities, remember, you need to change the direction of the inequality. So if I multiply by minus, that's going to be pi greater than x greater than 0. And on the other one is going to be 0 greater than x greater than minus pi. Which, if you write it in the same manner, because you got to combine these, remember, as my first example, the first piece is going to be this. So it's going to be minus x. And I'm going to write this in the other way around, right? So 0 greater than x greater than minus pi. That's like minus pi less than x less than 0. Same thing. And then 0 if x is between 0 and pi. So change the sign of x and then write the output of f of minus x in the same manner as f of x, because you need to combine these and you have to add them on each sub piece of the domain, right? So if I have to come up, like for example for g of x, if I have to add f of x plus f of minus x and divide by 2, I need to take both cases on the same interval. So on the first subinterval, on minus pi and 0, the sum of the two will be 0 plus minus x over 2. And on the interval 0 pi is going to be x plus 0 over 2. So therefore the even part is just going to be minus x over 2 if x is between minus pi and 0, and x over 2 if x is between 0 and pi. All right, so that's the even part. I'm sorry. What do I want to say? Yeah, that's the even part. Yeah, that's the even part. You can make the graph. It looks like a V. And then the odd part is the difference of the two. So just like before, f of x minus f of minus x is going to be 0 minus minus x over 2. And then x minus 0 over 2 if x is between 0 and pi. And if you look carefully here, you don't need to take a piecewise definition here, because in both cases is x over 2. So as it turns out, h of x is just x over 2 together. It has the same format in between minus pi and 0 and between 0 and pi. So that is going to be the odd part. So when it comes to write the Fourier the Fourier series for the function, once you compute the even and the odd part, at this point all you have to do is to add the cosine series for g of x above plus the sine series for h of x. Now, in both cases, remember, it's sufficient to look at the right half of the interval, right? So it's basically, we're looking now at the interval 0 pi in both cases. So this is the time when you can look at the previous notes, or you can look at the book, the table of series on the book. And we have a Fourier cosine series for x, and I need x over 2. So I'm going to just basically divide by 2 the Fourier cosine series for x, and from the table, that's pi over 2. I'm going to write it down exactly like it's given in that table. Cosine of 2n minus 1 x over 2n minus 1 squared, because remember the discussion is given in terms of odd coefficients only, because the rest of them is 0, but that is kind of annoying when you have to combine the two. And then plus 1 over 2, the sine series for x, which is summation from 1 to infinity minus 1 to the n plus 1. You look at the table for the... so actually it's 2 outside, right? So 2 summation from n 1 to infinity minus 1 to the n plus 1 over n sine of nx. You can leave it like that, although you can make some substitutions here, some simplifications, and again, it's better to write the summations to agree with each other. So that's why, for example, it's better to take the equivalent for the sine series of g of x to be to all the numbers, not just the odd numbers. So here you can have, let's see, 2 over pi plus 2 over pi. That's the another version for the same series, with minus 1 to the n minus 1 over n squared cosine of nx, plus the summation from 1 to infinity minus 1 to the n plus 1 over n sine of nx. This is because in this case you can combine the two series later if you want to. But to summarize here, in the formula, a naught, the constant on the outside, was pi over 4. The an, if you look at the coefficients, is 1/2 outside times 2 over pi. That's 1 over pi minus 1 to the n minus 1 over n squared. And then bn is minus 1 to the n plus 1 over n. I don't want to start a new page. I'm going to put them here. So essentially, once you come up with the coefficients in the series, then it's not that important to actually simplify it or to combine it. The coefficients are important when everything is said and done, basically. So with that, I think we'll leave it at that, and we're going to have the next lecture to go over all these formulas for sine series, cosine series, and Fourier series in general, like we have it in this class, and more examples involving the tables. And then probably after that, we're going to deal with how we extend it to other intervals than just minus pi and pi. It's just a very simple modification to deal with that. So that's it for today.